Great. Thanks so much, Kathy. All right. Hi, everyone. I'm Anthony D'Agostino. As Kathy said, I'm going to be presenting a chapter from the book titled Causal Inference in Counterfactuals and Earth Observation Research. This is jointly produced work with my colleagues Faraz Usmani from the Global Energy Alliance for People and Planets and Eleanor Benamy at Virginia Tech, who's actually in the other room presenting right now. So next slide. Go ahead. Great. So before I get into the specifics of the chapter, I thought it'd be helpful to first situate where it sits relative to the other chapters in the book. And this gives you a little bit more context as to what the purpose and the audience of this specific contribution is. So there's three groups of chapters in the book. We're in the second part, Methods for Spatial Causal Inference. It begins with a chapter on collecting ground truth data. I think that's a really good segue into our chapter, which is on counterfactuals and a kind of gentle introduction to impact evaluation methods. Then my co-presenters here are going to be presenting further deep dives into specific methods. So we're essentially creating the overarching sort of infrastructure, the foundation of the concepts, terms, and objectives of impact evaluation, and then other folks carry that on to further depth. I do, before continuing, want to say that I presented this chapter at the conference last year in Paris, got some excellent feedback from attendees as well as from reviewers who've been contributing to the book project as a whole, and just want to say my thanks to those folks for strengthening this work. So there's three learning objectives that we have with this chapter. We're anticipating that readers, after they've finished it, would be able to identify the most appropriate causal inference method for a specific implementation context that they're considering. They should be able to understand what the key considerations are when using remotely sensed data to run a geospatial impact evaluation. And they should be able to articulate how it is that remote sensing data can broaden and deepen the scope of research questions. So a couple of things that I think are important to call out about our approach. One is that we really presume that readers don't have any social science background. So we wanted to make this an exceptionally accessible text. We're really defining concepts up front and not assuming that folks understand what a null finding is or what a standard error is. We address concepts that are relevant to most or all of the subsequent chapters. And this way, folks can get that concept in a single chapter instead of seeing it repeatedly in each of the subsequent methods devoted chapters. So this is just at a high level how we've organized things, and it's also sort of the sequence that I'm going to be following as I go through this talk. Really providing an introduction, some initial fundamental concepts up front before then jumping into an overview, probably like a 20,000 foot or 7,000 meter level view of each of those individual methods. So I think it's helpful to go back into the history books. We want to first think about where the introduction or the origin of causality and the quest for developing causal relationships comes from. And I think it's obligatory for us to begin with that adage that everybody hates. Correlation is not causation. And the reason that that needs to be said is because it's not universally understood. Folks see relationships and assume that there's some relationship between two quantities when in fact there might not be. So one example that we use in the book is taken from Tyler Vigen's Spurious Correlations. If you guys haven't seen this website, it's fantastic. It is a data-derived trawling of correlations between two quantities that have no relationship with each other whatsoever, and yet have exceptionally high correlation coefficients in excess of 0.95, 0.98. So in this particular example, which I think is appropriate for the folks in the room and for readers of the book, is what is the relationship between the popularity of the first name Harmony as a daughter's name in the US and the number of associate's degrees that are awarded in agriculture and natural sciences. So you take a look at this relationship over time. We see a U-shaped sort of curve between the years 2011 and 2021. The fact that these things are related and that they produce the same pattern is absolutely arbitrary. There's no causal relationship because there isn't a conceptual linkage between naming your child Harmony and the frequency of these degrees. So that's sort of laying the groundwork for understanding that if X causes Y, there should be an ability to articulate why that happens, a mechanism. And that's really the cornerstone of causal inference methods. So in our very quick review of the history of causal inference, we start in the 1800s with an experiment that James Lind had conducted that's often really considered as the first published RCT that was ever conducted. So James Lind was a physician, and he was trying to understand how to address scurvy. So you'd have sailors, setting out to sea, they'd be gone for weeks and suffer, scurvy and not have any cure. So what he had done was create a multi-arm treatment where pairs of sailors would be given treatments like cider, garlic and horseradish paste, vinegar, all presumed cures for scurvy, but hadn't yet been really studied or analyzed. What he found was that one treatment arm was exceptionally successful in curing scurvy, and that was 2 oranges and lemon. So we understood that there's a relationship between citrus fruits and curing that particular disease. We spent a little bit of time talking about the Rubin causal model. Donald Rubin was a statistician who had created this workhorse model for thinking about causality back about 100 years ago. And just at a very basic level, we can think about 2 quantities. There's an outcome of interest. That's the thing that's our left-hand side variable. And there's a treatment. So let's take an agnostic example. We want to understand whether or not a particular medicine, maybe it's acetaminophen or ibuprofen, is effective in reducing fever. So we might want to understand for your specific child, what is the effect of that medicine? You care most about your son or your daughter, and identifying sort of 2 comparisons. If your daughter takes the medicine versus not taking the medicine. So AI enables us to kind of think about these 2 scenarios, with the only difference being the image in the middle. Your child has the medicine, and one where your child doesn't. Now, the problem is that there's this thing called the fundamental problem of causal inference. Your child can't simultaneously take medicine and not take medicine. It's choosing your child is adopting one of those states of the world and not the other. If we're to focus more specifically on sort of the topics and sectors within this room, let's consider an alternative example. What is the effect that intercropping has on productivity? And again, I'm interested in specific examples. What is the effect on my plot? Not just in general. Now, the problem is that your plot is either intercropped or not intercropped. We don't get a chance to see it in both states. So that really motivates this central premise, which is instead of looking at individual treatment effects, we need to think about average treatment effects pooled up across multiple observations who are either exposed to treatment or exposed to control circumstances. So this really sets the stage for establishing a counterfactual. What would have happened to a person, a plot, a country in the absence of treatments? And then identifying what are the assumptions required under which that counterfactual holds. So we have this nice little illustration on the right. This is a directed acyclic graph to really sort of expound on the complexity of understanding these relationships. It's not just the fact that we want to compare intercropped and pure stand plots. It's the fact that there's a host of other factors that complicate that study. So for example, maybe it's the case that small plots enjoy high levels of labor application because they have little outside opportunities. So maybe when we observe an intercrop plot, we're actually seeing plots that have higher labor rates, and that's the factor that's driving changes in crop yields. It can also be the case that plots that are irrigated or are more likely to be intercropped. And so instead of simply observing the difference between intercropped and pure stand plots, we're seeing the differences between irrigated and unirrigated. So the purpose of causal inference and these impact evaluation methods is to be able to conclusively and very sort of convincingly establish a relationship between your treatment and your outcome after having controlled for some of these confounders or other factors. So for folks that are not social scientists, there's a lot of new material here. There's a lot of new concepts. And part of the objective of the chapter is to make this accessible. So with all of these concepts, we try to go to great lengths to ensure that they're defined, that they're elementary, that they're simple, so that folks don't get sort of discouraged by having to walk into a new language and not really having sort of the equipment or the machinery to navigate and make sense of things. So for example, throughout the chapter, we have different boxes that provide those definitions in an easy to search way so that folks really understand what is at the root of creating these concepts and of these methods as a whole. So I think as you've all seen from the presentations yesterday, as well as some of the journal articles that were shown today, that there's many different ways that a geospatial impact evaluation can be run. So here, let's just take a really basic regression equation and boil it down to three pieces. There's an outcome, there's a treatment, and there's some observable covariates. Now, I think that we, as authors of the chapter, want to take a more sort of open stance on what qualifies as a GIE. So at the top, and again, apologies, there's a sort of Google Drive and PowerPoint issue affecting the formatting, but you can imagine a study in which the only EO variable that's included in your study is the left-hand side. So there's a change in forest canopy cover. You're using, say, GFW data from WRI, and that's the only EO product that goes into your analysis. There's another version where you combine both the treatment status, let's say fire exposure, you take a VIIRS product or a fire burn scar product to identify which pixels or locations have been affected, and you're also taking a look at vegetation cover. So now we've got two forms of EO data that go into your regression, into your impact evaluation. And then the third one that I'll describe is one in which every single data source in your study comes from remote sensing from Earth observations. So let's imagine we're interested in, again, locations that have experienced fire, whether or not those that are closer to roads or further away from roads have faster vegetation recovery. So this is an exclusively satellite-based analysis that can be done in an impact evaluation framework, and there's no administrative data, there's no household surveys, no phone calls. So again, kind of just zooming out, there's many different flavors and degrees of intensity with which EO data can be incorporated into an impact evaluation. We want folks to recognize that it's not as if, you know, every key data source in your study needs to be from a satellite. So we spend a bit of time going into the individual methods. We begin with experimental, and that's going to be our randomized control trial. As you'll see from the subsequent slides, we wanted to use a series of graphics to illuminate and sort of make clear what's happening, how the distinction between treatment and comparison is made under each of these methods. With the RCT, this is really considered to be the gold standard and most approximates the standard scientific experiment that we're familiar with typically from pharmaceutical research. So in advance of an RCT, there's a bit of work that the researchers need to do. You need to run power calculations and figure out your sample size. You need to determine whether or not your unit of treatment is at the unit level or it's at the cluster level. And these illustrations show two different variants of that. So one is which, you'd have a series of households across multiple villages. You're randomly assigning households into treatment or control, as shown in green and red, or alternatively, where that level of randomization happens at the village level. And so depending on which village or cluster a household is in, they inherit the treatment status based on that higher level geographic unit. Then moving over to matching methods. Under matching, the researcher has a lot more control over selecting a comparison group. This is both powerful, but also challenging because there are these research degrees of freedom that can be used as well as abused. So for matching methods, we provide a little bit of a description about the different diagnostic approaches as well as overall methods. There's K nearest neighbor, there's coarse and exact matching, there's propensity score matching. There's many different flavors that exist. And this chapter is not the destination for getting into the details of all those specifics. It's the entry point. So for folks that didn't know that matching existed and it was an option to find a comparison group in an ex post evaluation, we wanted to open the door and let folks know that that's a possibility. Diff and diff, we've seen a few examples from the presentations yesterday and today. We start with the basic two-period model and then get into the more advanced work of a staggered adoption, Callaway-Santana estimator, and being able to really motivate what does parallel pretrends look like and the power that EO offers in giving you many years of data to assess whether or not a parallel trends assumption can be in fact defended. Just a couple more methods that I wanted to kind of quickly go through. We spend some time describing a regression discontinuity setup. The first example is non-spatial. There's simply a cutoff level that differentiates folks that receive treatment from folks that don't. That could be like a scholarship that's predicated on receiving a specific score on a standardized test. And then we move into how that framework can be applied into a spatial setting. Folks who are just upstream or just downstream of some sort of intervention of interest. And then lastly, Ariel had presented yesterday on a synthetic control method study. One thing that's fantastic about synthetic control is that you get quantitative rigor under a condition under which a small number, possibly just one unit, receive treatment. So for each of these methods, we're just offering the introduction. We're helping people understand the basics. What are some of the core identifying assumptions that apply to each? We want to leave them with a series of resources so that they can then go off and find more detailed and more updated material. Each of these methods is in motion. And so, it's important to recognize that these methods are evolving as anybody, especially in the diff and diff world, has seen over the last decade. Just a few things that I wanted to close off with, challenges and opportunities. Much of this was echoed in yesterday's presentations, and so I wanted to highlight just a few of them. So some of the strengths that EO offers is that the researcher has exceptionally fine control over your treatment area. So in the example that I mentioned before, where we want to understand fire dynamics, we really could limit ourselves to just the pixels that experienced fire and what happened in those specific pixels. Researchers typically are beholden to the level of data collection that governments or that some other entity has commissioned, and that would be at the administrative level or even at a national level. There's also very little marginal cost for accessing imagery of broader areas. So let's say that you wanted to conduct a matching study, and in the immediate geography that you're working in where treatment occurred, you're not finding good matches. Because images are relatively free, you can expand that area and potentially find excellent matches in a broader geographic space. So just in the interest of time, and unfortunately, the top couple of images are not very clear to see, but there's some important challenges that folks should keep in mind, regardless of which method that they're applying. The first is that we're often trafficking in indices and proxies, not the thing that we actually care about. So for example, there's been a lot of work done on using EO to understand agricultural productivity. When we're talking about agricultural productivity, we're typically thinking of tons per hectare, some physical quantity that's produced. But the remote sensing models that we're generating are calibrated models that predict that, but really only provide us changes in vegetation indices. So whether or not those models are accurately recovering physical changes in productivity is a question where, the models are improving, they're getting better and better, but at the end of the day, it's a vegetation index signal that you're extracting. A second big challenge is that just because data is available doesn't mean that it's in fact suitable. And I think especially for economists, there's a big temptation to simply say, look, there's data available in my area of interest. I'm going to run with it. But the fact is that if you take some products, they're based on a very small amount of ground data. So in Niger, for the CHIRPS product, Niger is larger than California and Texas combined. They have 16 rain stations, and Germany has 2,200, just to give a sense as to the sort of discrepancy there. So in the interest of time, we just close the chapter with some synthesis questions to help readers understand whether or not they've like fully grasped the material. And I think that's a great segue to get into the other chapters where folks dive into specific methods. So thanks so much.
Ajay. Thanks, Anthony. That was great. So we're going to move on to Ajay Shenoy. He is an associate professor at the University of Santa Cruz. Over to you.
Thank you. God forbid I not be heard. Thanks, thanks everyone for attending what is possibly the densest session in the entire conference. So Anthony did a fantastic job introducing all these concepts that I will not have to spend a lot of time on. I can now assume you know why I'm using the word treatment and control. Uh, the big challenge I think for all of us writing in this textbook is the sheer range. Both the challenge and the opportunity is the sheer range in the audience. And so I happen to be writing this with my two colleagues, Julian Martinez Yarate and Michael Lung, who are both econometricians. And so the chapter includes a very, very math-heavy section on inference, et cetera, like the exact formula. If you are using it and you are totally not interested in that, I just want you to know you can skip over it. But if you want the formulas, they are there. So you, as a reference, I'm not going to talk about, I'm going to avoid, I think there's like one equation in my entire talk here today. And so that's the flavor I'm going with. So I want to start this out just thinking like, what are the types of questions you can think about here? So suppose we want to estimate the damage caused by a hurricane relative to the places that were not hit by the hurricane, right? Or if we want to know whether a brush clearance program reduced the risk of wildfires, whether a highway caused deforestation, or if we want to estimate the impact of regional development policies targeting a newly formed state, right? So what do all of these situations, varied though they are, have in common? Well, there is a event or a policy with a discrete start, right? So a hurricane, there's a point when there was no hurricane, and then there was the hurricane, and now we are post-hurricane. Likewise, with the highway, we can imagine there's a clear point before the highway arrived, and then a clear point after it arrived. And second, that it affected some areas and not others, right? And so that's sort of the distinguishing feature, the basic conditions you need for a difference in difference, right? Those are the two differences, the before and after, and the treatment and control, right? And so one approach you can take to this is spatial difference in differences, right? Difference in differences is a general method. Once you put it into a spatial context, that's what makes it spatial. And so what distinguishes a diff and diff, and spatial diff and diff in particular, from any other kind of simple comparison is that it's comparing changes, right? That's what that first difference is involving. So we want to measure the differential growth rate between a treated and control area, right? And so we're able to control for baseline differences. So the general idea, as in any impact evaluation, of course, are comparing treated and controlled, and then the diff and diff is just considering the idea that you are comparing before and after the policy. Now, what makes it spatial is that the treatment has some kind of spatial variation, right? Like, so in the hurricane example, obviously the hurricane doesn't teleport around at random. It follows a certain path, and there's a spatial component to that path. Now, one consideration I'll talk about a little bit more is that there is a thing that is being affected and that you are measuring. And so there are certain units. Those could be administrative units. So maybe you are working with data that has been aggregated up to like the district level or the census block or whatever. Or if you're using remotely sensed data, because that is constructed at the level of a geospatial pixel, you could potentially use those individual pixels as units, or you could define a grid of what's called like a fishnet, and then aggregate to that, right? And so these are to some degree things that the researcher can consider. But in general, you are always going to have some kind of grid cell. Is Clicker has died on me. Okay, there we go. 15 clicks. All right. And so where does the Earth observation data come in? It's just a very valuable resource. So I think like we've had a dozen people say at this point throughout the past couple of days that the real value of this Earth observation data is that it's generally measuring the entire planet in a sort of comparable way. I use the word sort of because I'll talk in a little bit about all the crazy stuff that happens with different satellites and whatnot. But in general, it's not like if you're talking about census data, for example, the way it's collected in one country versus another could be completely different, right? The way things are defined could be completely different. Whereas you use nighttime light data, that light emission index is going to be essentially similarly defined in different places, right? And so it gives you a comparability across space, and you generally have it measured. It just every time there's a satellite flyby, conditional on how exactly the data is processed, right? So it creates a lot of opportunities for a diff and diff in particular, and potentially varies fine spatial resolution depending on which satellite you're using. And so you can measure things like economic development. So nighttime lights were one of the first applications that became very popular with economists, at least. Probably other fields were using other forms of spatial data long before that. And now more recent work has used fires, measured fires, and used that for impact evaluation. You can measure pollution, vegetation indices, urban development. I've seen projects measuring illegal mining using satellite data. And there's many, many more, right? Like the whole point of this conference is to show you all the things that are not on this list as well. All right, so the basic idea behind diff and diff, right? Like let's step away from spatial for a minute and just very basic diff and diff. So Anthony mentioned this idea of parallel trends. So the idea is you have, let's suppose we just have two time periods, make it very simple. You have an outcome and it's evolving between period 0 and period 1, right? From 2026 to 2027. And you have a control group that actually evolved along a certain path. And now we want to imagine a world in which what we call the treated group had evolved in the world in which it had never been treated, right? So you can imagine we have this hurricane, it was going to hit certain areas, and then, due to some act of God, a tablet falls from the sky and the hurricane is canceled, it never hits anybody. And the treated groups evolve in this way. That's sort of parallel, as you can see, to the control group, right? That's the counterfactual we want to imagine, right? And that's the counterfactual that diff and diff requires, that in a world in which the hurricane had never happened, the highway had never been built, the brush clearance had never happened, it would evolve in this way. Now, because of the treatment, instead, you have this deviation from that, and the entire deviation from that parallel trend is caused by treatment, right? That's what's called the parallel trends assumption, right? And so then given that assumption, we can sort of measure this difference. So we are able to, the fact that we have a different intercept doesn't matter. That's what diff and diff is designed to handle. You could have different intercepts between all the different units, and diff and diff will take care of that as long as you have these parallel trends. And then we can measure, we can approximate what the treated counterfactual is with the control counterfactual, and then take those differences. And the beta you estimate between them is the treatment effect, right? So that's the general idea behind a diff and diff, right? Any diff and diff. What is a spatial diff and diff? What happens when you come into space? So normal DID, which is going to be familiar to all the economists, certainly, and a lot of other policy eval experts, is usually you imagine some kind of, not necessarily a random sample, but at least a sample that's sort of spread out, and spatial correlation is generally kind of low to the point where you don't have to necessarily worry about it. It's not that treatment is in any way correlated with space. Whereas with a spatial DID, oftentimes you have enough geographic clustering in your observations such that you will have to worry about spatial dependence between observations, right? And so when you're using satellite data, for example, your pixels by construction are right next to each other, right? And not only the outcome spatially correlated, but sometimes your treatment is going to be spatially correlated as well. And so that creates issues in a number of ways. Now, it creates advantages. It creates opportunities in that because you have this notion of space, things that are close together are more likely to be evolving on parallel trends, right? They're exposed to similar conditions. And so your identification assumption, your most important diff and diff identification assumption is more likely to be satisfied. But there are complications. So one of them is spillovers. I'm not going to spend as much time today talking about spatial spillovers, but the book chapter talks about this in some detail and has an exercise that deals with it as well. The one I will talk about a lot more, which comes up literally anytime you're doing this, is spatial inference, right? So how do you know basically how many stars you've earned, given the fact that your error terms are in fact correlated in a way that violates sort of the usual assumptions. So the way the chapter works is, thanks to some helpful suggestions from both our reviewers and the editors, we have sort of a roadmap that can be used as a guide for like step by step. What do you want to think about as you are doing a DID? And I'm actually just going to follow this roadmap today in the example that the chapter considers. We have this one running example, and we try to illustrate everything that you would do in a diff and diff based on that example, just to make it very concrete, right? Like getting away from the equations as much as possible and thinking about in this concrete application, how would you do this? So the first thing you want to do is define a treatment geography. That really means like basically what is the area where we have our treatment and control? And then what is the unit of observation, right? I talked about this a moment ago, and you're going to have to do this every time. I'll show you in a moment what that looks like. Then you have to actually choose who is the control group. Generally, you know who the treatment group is, right? Because you're evaluating a program that's going to determine who the treatment group is. The question is, what is the control group that would satisfy the parallel trends assumption, right? You have to choose it very carefully to make sure that parallel trends assumption holds. Then you're going to put together your data. And what I'm going to talk about specifically is what kinds of remotely sensed data could be used. So that's what you want to think about. How to aggregate it. So you have your units here, and that's going to some degree determine your aggregation. Depending on the aggregation, you may have to worry about certain issues that will come up. In particular, when you're using remotely sensed data, you can have certain issues arising from satellite measurements that I'll talk about briefly here. Design can help with dealing with those types of biases, but you want to be mindful of the product that you're using and what kinds of biases you can expect from the satellite data. Then there are different methods you can use to check for parallel trends, right? So again, you can never directly test the parallel trends, or rather you can never prove the parallel trends assumption, but there are some falsification tests you can apply that I will show you that are helpful in general, right? Finally, fun part, you estimate the treatment effect, so you run the regression. And usually for spatial diff and diff, that really just comes down to what fixed effects you want to include in there, which is basically what kinds of dummy variables do you need to control for to make comparisons both within unit over time and then between units period by period. Then finally, now that you have a treatment effect, you want to know whether it's statistically significant. That means calculating the standard errors, so doing the inference. All right, so the application that I'm going to run through here is the state of Uttarakhand. So what happened here? So this is a state of India that was formed from an existing state. It sort of seceded from that state in the year 2000, at the end of 2000. Then basically a year and a half after secession, there was a policy applied to that state to sort of help it develop. And so it received these major tax breaks for new firms that were founded. It received these big infrastructure grants, and then subsidized electricity access. And so if we wanted to evaluate, this is a concrete policy, it is applied to a concrete area, what would be the economic impacts, right? So if we want to know what would be the impact on a proxy for GDP, for example. Let's suppose this is the DID application we want to do. So steps 1 and 2, remember, we have to figure out the treatment geography and the comparison area. So the outcome that we can consider here, the classic proxy for economic activity is nighttime lights, right? And so the intensity of nighttime lights is strongly correlated with GDP. This has been shown going back to Storygard and Weil. And so we're going to use as our comparison state the old state that this was formed from. So you can see you have this new state that was formed. This is the one that got the policy. It was formed from this bigger state down here. And so this is going to form our control group. And so the boundary between these is our treatment cutoff, right? So here we've defined our treatment geography. Now we want to think about what are our units of analysis. For the purpose of this chapter, we are going to use these cells defined in a fishnet. So we're not going to use administrative boundaries. We're going to essentially define these cells and then aggregate within those. And then restrict to cells within 10 kilometers of the boundary. And since both sides are part of the same state, they're probably on the same treatment trajectory, right? So we're going to use their proximity to help us with our design. Now, and this is what you see, this is what happens to the data once you aggregate it into the sets. All right, so what's the panel data? We are going to use DMSB. So this is actually a very old satellite data just because we want to go all the way back to 1992. So this is based on a paper published in 2018. So back in old time days when I actually wrote the paper that this was based on, it was really up to 2013 that the data was available. And so despite this fact, there are actually 6 satellites because this is over 22 years. And I talk a little bit about this in the chapter. So we discuss this issue of when you have different satellites looking at the same thing, you can have different measurements, right? I don't want to get into huge detail here, but really there can be substantial differences in what the different satellites see, even when they're looking at the same thing at the same time. So you want to think very hard about whether that's going to mess up your design. Now, what's great is that if you have a well-designed difference in differences, because it is intended to have parallel trends between treatment and control, you would expect it to have parallel trends in this measurement error, right? And so design actually solves a lot of this problem if you are careful. What you just need to make sure is that you don't have a design where treatment is correlated with the measurement error. All right, so then you want to check for parallel trends. And so really, there are 2 classic checks. One is whether they are on parallel trends on the same trajectory before treatment, right? And again, we had a number of folks yesterday saying very correctly, I was so glad to hear it, that this is not the same as proving you have parallel trends. It is merely a necessary condition. You want there to be parallel trends between treatment. Why is it not sufficient? Because you could, for example, have confounding events that coincide with treatment, right? And so one way to check for this is to use a placebo test. A placebo test is any situation where you have the same confounding thing or potentially confounding thing applied to a similar area that did not get treatment. And so if you see a treatment effect on this thing that didn't get treatment, it suggests you have a problem with your design. And so here in the case of our example, we can look at the raw pre-trends. This is just the time evolution of treatment and control. You can see they are on very similar trajectories until the policy begins, and then they start to diverge. And so if we actually estimate this in an event study regression, which you can consult the chapter for the exact equation, this is the actual difference. And so there's always an excluded year where everything is the change relative to that year. And so you can see you have this growth, these positive effects that arise afterwards. Now, the question is, what about a confounding effect from the formation of the new state itself, right? That's the big thing you might worry about in this case. That would violate parallel trends after the treatment. And so the placebo test we can use here is to look at a state that was created at the same time, right? So there were 3 states in India created at the same time, but only this one, Uttarakhand, got this treatment. This one, Jharkhand, was created but did not get the policy. And so if we run exactly the same design on that state, you can see there's essentially no impact, right? So this is the kind of placebo test that can be useful in supporting the parallel trends assumption. Meanwhile, one thing you can think about is suppose we hadn't restricted to areas that are near the boundary, that are spatially close by. Suppose we looked at things that are further apart. You can see parallel, like the pre-trends are very different, right? And so this immediately demonstrates you don't have parallel trends, right? And so research design does matter. And again, that spatial component is really useful in getting good research design. All right, yeah, you can run a regression, estimate the treatment effect. That's very easy. Let me just briefly say something about inference. So you can have correlation in the error terms across both space and time. And that creates problems for inference. So what can you use to deal with that? So if you draw these types of correlograms, which show you how much the correlation between residuals fades over space and time, that can give you a guide to whether you can do things like spatial hack or clustering. Again, refer to the chapter for more details on this. The other thing that's useful is to run Monte Carlo simulations. So yeah, I won't go into a huge amount of detail since I'm essentially out of time, but this is a way to just measure whether you're estimating too many false nulls. All right. So just to quickly summarize, so these are the kinds of steps you'd want to go through that I just talked through. And some extensions that we don't want to get into too much in the chapter, but we'll leave you as information is the staggered treatment. So if you have treatments happening at different times, not all at once, there are methods that you can refer to. There's another chapter on difference in on discontinuities, and you can combine that with a before and after to create a different discontinuities. All right, I'll stop there.
Awesome. Thank you so much. We're going to move on to Kendra Walker. She's a remote sensing specialist at MLab. Go ahead.
All right. Oh, clicker. All right. Thank you. So I co-wrote this chapter on designing randomized control trials with my colleague, Kelsey Jack. So Kelsey Jack is a development economist, and I'm a remote sensing specialist. Together, we have collaborated on several projects trying to apply remote sensing data to randomized control trials retroactively. And we have gained many insights from that collaboration. We were kind of curating a list of guidelines, I guess, online that we had colleagues contribute to. And so we had this kind of online thing with a lot of interactive whatever. Anyway, we have tried to wrangle this into a chapter. And thanks to the GeoField conference last year, I got a lot of feedback on it, and I think hopefully it's now a smooth chapter that reads smoothly, but it's been a lot of wrangling. This chapter is targeted toward an RCT designer, really, who might want to integrate remote sensing data into the RCT. So hopefully Anthony's chapter is giving them somebody who wouldn't be an RCT designer, a lot of the background they might need to know. We did add some components based on the last convening feedback we got to kind of give more information on RCTs in general. So a remote sensing specialist could get more out of it from that point of view. But really our goals are that after reading the chapter, the reader will be able to recognize areas where RCTs can benefit from remote sensing data, but also understand that remote sensing data does not always enhance an RCT. And so they need to be able to assess the likely power gains or lack thereof from using remote sensing data to, especially if the goal of that is to augment primary data collection. And then also need to be able to anticipate situations where bias might be introduced by the remote sensing data, because generally RCT designers are very concerned about bias. That's kind of the reason you would use a randomized control trial. So we want to reduce that bias as much as possible, and know what types of primary data are needed to make the best use of remote sensing data. So from my point of view, that's really, I'd hope the biggest thing somebody takes away from this chapter is the need for primary data and the structuring that primary data to be most useful, to be able to garner the insights from remote sensing data. So we did add an introduction to what a randomized control trial is based on feedback from the last session. I think Anthony's diagram is a little prettier than ours, but the basic, for those who aren't familiar already with randomized control trials, you have a study population, and then it's randomized into control and treatment units. And then there's an intervention period where the treatment is applied, and then we observe the outcome. And sometimes you observe the outcome directly on the randomization units, but often you have a cluster design where you're actually observing the outcome on a smaller component. So if the randomization unit is the village, maybe you're just observing a subset of farms within the village. But the key point of RCTs is because they rely on prospective design. You're planning in the randomization, unlike natural experiments. So you have this design phase regardless, and then you have an opportunity really to design it thinking of the remote sensing data and to collect the data, because there's going to be somebody in the field during the implementation phase. I'm not aware of any randomized control trial that has remote implementation. So there's going to be somebody in the field, and when those people are in the field is a great use of time to really maximize gathering data for the remote sensing component as well. So this chapter is really structured around the three main reasons that somebody might want to add remote sensing data to a randomized control trial, because each of those reasons has its own set of considerations. So one big reason is to increase statistical power. We know that getting ground data is very costly, so it's often cheaper to get observations from remote sensing data. And in many cases, that can increase statistical power, but in some cases it doesn't. So we need to look at that. And also in the case of subpopulations, sometimes it's hard to reach certain populations. There's extreme violence or other things going on that we want to have observations for, but we just can't get out there in the field, which creates a set of issues that we need to consider. But when that's considered, maybe the remote sensing can add to the project. Often a reason that people want to add remote sensing data is to increase the set of measurements. So sometimes remote sensing data does produce higher quality measurements than you can get on the ground. And often survey methods produce bias. People will tell surveyors what they want to hear. They'll say, yes, we're implementing your project. We're doing all the things you told us to do. Sometimes you want to observe that remotely and see what's going on. Or in the case of illegal activities, the opposite. Maybe people will tell you they're not doing things that they might actually be doing because it's illegal. And then the third common reason for using remote sensing data is to extend the observations spatially or temporally. So to look for spillover effects, or to be able to look for long-term effects, that you can't continue the randomized control trial forever. You can't continue going out in the field forever. So you have this opportunity to extend. So looking at the first motivation for increased power, economists really like to do these kind of power exercises, and we have some some tools in the chapter if people want to play with them. The key here is that the assumption is that we know what the error is in the remote sensing data, which honestly you don't usually know ahead of time before you've taken measurements from the field. But if you did know the error in your remote sensing data, then you can look at what kind of power you would gain from adding more observations, or sometimes lose. If you have high error, you might actually lose power, in which case you don't want to add remote sensing data. So these are tools that economists might use. And then we also have this indifference curve, same idea basically. If you have a sample size on the ground with assuming no error, what kind of sample size would you need from a remote sensing measure that has a degree of error? It's basically what that, and you can look at the indifference for whatever power level you're willing to accept. So a bigger issue really for adding remote sensing data is that it can add bias. And so if it's adding bias, then the power really doesn't matter. That's really all this is showing. The power doesn't matter. You're going to have biased effects and you're going to miscalculate your true effect anyway. So it's very important to consider biases when adding remote sensing data to a randomized control trial. The main point that we would like our reader to get here is that primary data are needed to train and calibrate any remote sensing model, or at the very least, to validate the remote sensing model. So if you're using a pre-existing model, you need to validate that locally to know what the error is and whether the error is biased for your different groups. Bias can occur anytime since units estimated with the remote sensing model or when units estimated with the remote sensing model are not as well represented in the primary data as others. So if you have your treatment or control, one group is better represented than the others, and when you're training the model, you can get a biased model. Also, if you're looking at certain groups that have more data and you're trying to extrapolate that to other hard-to-reach groups, you can introduce bias there. So throughout the chapter, we referred to many examples of what we're talking about. We have two key case studies that we refer to repeatedly. One of those is this study. It was an RCT that Kelsey Jack and her colleagues conducted in Punjab, looking at whether paying farmers to not burn their fields had any effect on whether or not they actually burnt their fields. And I joined in later to do the remote sensing component, although they had designed this with the idea that remote sensing would be applied to it. The key issue here is that although it might be easier to measure burning using remote sensing data than on the ground, in the case of crop burning, it is really not a trivial thing at all to measure it, even with remote sensing data, because this graphic at the bottom here is showing a typical plot that it gets burned on the 4th of November there. In an image on the 5th of November, you could still see that it's burned. And then on the 6th of November, it gets tilled. So with regular data, it's hard to see any difference after 2 days of burning. With Sentinel data using like the mid-infrared bands, you can kind of pick up the burn signal still, but within like 4 or 5 days, you've completely lost the burn signal on these fields. So you can't tell the difference between a plot that was burned and tilled and a plot that was just tilled. And so this becomes an issue. With remote sensing data, we ended up using planet data here that you do get nearly daily views, and so you can kind of figure out what's been burned or not. But with Sentinel data or other freely available data sets, it's near impossible to figure out which fields actually got burned. They had ground data, but the problem is that they had more ground data, a lot more ground data for the treatment units than the control. So we need to train a model, we need data for both the burned fields and the unburned fields. And the issue is really figuring out what fields didn't get burned. And the treated units were receiving payments, so they were entering into agreements with the investigator. So they had to show the investigator that they had managed their crop or their residue in a way that, in an alternative way. And that would be costly to do if they were going to burn it anyway. So they wouldn't have done that. So they called, once they had it all managed, then they called somebody to come check it out. And so they could say, okay, this plot was not burned. On the other hand, the control units weren't getting any money. They had no incentive to do anything like that. So they did not provide that data set. So we have no burn labels for the treatments, but not for the controls. And so in just training a model, there's a potential for bias there if, the key is if, that there's a difference in how the treatment group is acting compared to the control group. So if the payments to the treatment group are causing them to do something different, like maybe they have money, so they're managing their crop differently than the control group does, or they're growing different things, or they're using different machinery, and then the model might pick up burning differently for the two groups, which would then cause bias. So this is an issue we struggled with for a long time and kind of go through repeatedly in this chapter. There's also clearly biases when you're a potential for biases when you're measuring spillovers or long-term effects. This is in no way specific to randomized control trials. This is really an out-of-sample measurement issue, that anytime you train your model for one area and then you're looking at a different area, you need to consider that other things might be going on in the other area that could cause bias. Your trained model isn't going to see things the same way. And same thing, spatial spillovers, but also long range effects. Things can change over time, sensors change over time. There's a lot of reasons your model is going to change over time. Well, remote sensing data is definitely prone to these issues. It can also be helpful in the design phase to plan your spillover areas ahead of time. So you can use remote sensing data to figure out where you're going to want to look for spillovers, ideally, and actually collect some of that data when you're on the ground. So you at least have some data points to match to and to make sure that things are similar in those areas as your treatment areas and, well, your experimental areas. So the bottom line is really that the more primary data that can be collected for the additional time periods or the additional spatial areas, the better your model will be. And so the key here is to strategically collect primary data. So since you need some degree of primary data, we want that data to be as high quality as possible. And that considering the unit of observation can be very helpful for deciding how to collect the primary data. So your unit of observation could be at the pixel level if you're looking at something like deforestation. So you're looking like in a whole village and you could pick a subset of pixels randomly to sample for deforestation. If you're looking at something like a field, then usually the pixel is smaller than your unit of observation usually, and then you need aggregation or object-based methods. There's all kinds of methods to aggregate up when you have a lot of pixels. So that's a great situation to be in. But often, well, not often, but there are examples where the pixel is smaller. I mean, the pixel is larger than the unit of observation. So if you're trying to use like MODIS fire data to look at fields being burned, you're going to have multiple fields within a pixel. And it's impossible to sort out which field got burned in a given pixel. So in these cases, you might want to think about using like a block design and considering treated all of the fields in a pixel. And we haven't seen many examples of this, but I would like to see more because I think using a block design can be very helpful. Also in cases, even when you have smaller pixels, but you have a more vague idea of where the treated area is, so you don't really have crop perimeters. Using a block design to make sure that there aren't overlapping treatment and control areas is extremely helpful. And yeah, we want to collect primary data to best leverage the remote sensing data. So the key thing to remember is that we need primary data for a subset of units for both the training and validation of the model. If we get it for all units, then there's no need for remote sensing data. But we need to train the model with a subset of data, and then you can get more observations from remote sensing. But we need primary data to link all units, all of the experimental units to the remote sensing data. So meaning if your unit of observation is the farm, we need linkage data for all those fields. If we only have field perimeters, but we can't apply those to the farmers, for example, then yeah, you lose that information in the remote sensing model. So we go over in the chapter a lot about, the requirements for linkage data, and, the higher quality, the better. So if you can get perimeters rather than points, better. But if you can just get points, you can do things with that as well. So yeah, that's really the bottom line, that RCTs create a unique opportunity to integrate remote sensing based measures, but we need to anticipate the pitfalls in advance to make the best use of remote sensing data. That's it.
Great, thanks so much, Kendra. So we have about 6 minutes for questions. Sorry, it was probably my fault, mismanaged time, but
Sorry.
you guys are good. Does anybody have any questions? Yes.
Yeah, just quickly. First for Anthony, I really like the overview of the different model. I was wondering if your chapter you also provide some, recommendation on good practices as well. That would be very interesting. For Ajay, I was in a seminar at UC Davis very recently where they were presenting about cases on DID where the intervention is time bound. Instead of just being implemented at one time, it's sequentially over time. How do you ensure the parallel trend assumption to be ensured in that cases? Have you thought about anything like that? Yeah, and then last for Kendra,